Now that we have established the static stress conditions and looked at the stability prior to the earthquake, the next step is to move on to the dynamic analysis. And to begin with, we need to talk about the equivalent linear method. Conceptually, the equivalent linear method of analysis uses a linear elastic constitutive relationship. That is to say that the stiffness of the material is held constant as we move through the earthquake record. However, the soil stiffness is modified for each pass through the earthquake record. The soil stiffness, the G modulus that is modified in response to the dynamic shear strain. So to begin with, the first pass through the earthquake record, each element is assigned the specified G max or the specified stiffness, and then we seek to find the maximum or the peak dynamic shear strain for each element. So the dynamic peak shear strain is flagged for each element. So with the peak known, the soil stiffness is reduced according to a user-specified G reduction function. And so G, or the soil stiffness, is modified for each element. So what you will see during the process is that as we go through the earthquake record, the shear strain, we reach a point of a maximum and then keep it there until it gets higher, keep it there until it gets higher, and so forth. And finally, we reach a maximum value. So even though there is earthquake shaking after this point, the shear strain never exceeds this peak value. So the whole objective here is to find this peak value. The damping ratio is also modified in the same manner. And so after the soil stiffness and damping have been modified for each element, the analysis runs through the earthquake record again. So once again here, the same thing, shear strain, and so we have a damping ratio, and the damping tends to increase as the shear strain increases. More damping. Initially we have low values for damping, then the damping increases during the shaking. So the procedure is to repeat this until there is no further need for adjusting the soil properties. Repeating that, so there is no further need to adjust the soil properties. Usually this takes about 5 iterations. Experience has shown that there's little to be gained by going more than 5 iterations. But even 5 iterations is computationally very intensive. Say, for example, that the shaking record is 10 seconds with data points every 2/100th of a second. This makes a total of 500 data points, and with a delta t, or a time step of 2/100th of a second, this means we need to do 500 element analyses for each time we go through the record, the earthquake record. So with 5 iterations, this means that we are doing a total of 2,500 finite element analysis. So consequently, we need to be careful about the mesh size and the length of the earthquake record, because if we don't, we are doing a lot of we're producing a lot of unnecessary data, and it takes too time too much time and the analysis take too much time, and the files get unnecessarily large and it becomes difficult to look at the results. We'll return to this a little bit later. It is important, once again, that to recognize that we are looking for peak values. And the peak values often occur early in the shaking. So continuation after the peaks have been determined is of limited value. So if we have an earthquake record and we have some large, strong motion shaking, then this part of the analysis is kind of irrelevant because the peaks occurred in this part of the analysis. So doing this part of the analysis provides no additional information in the equivalent linear method. It just produces too much data that is of limited value. Once again, we'll come back to this in the next segment. So what we need to do for material properties for an equivalent linear analysis, number one, is to specify or define the soil stiffness. We do this by defining Gmax. Gmax is a small strain modulus. This implies a high magnitude. It's much higher than the corresponding Young's modulus suitable for a sigma W static analysis. The Gmax is often determined from seismic geophysical tests that measure shear wave velocities, and Gmax can be related to the shear wave velocity. There have been empirical relationships that have been developed from laboratory tests, and what we have done is we have incorporated these empirical relationships in QUAKE-W, and so we provide a series of sample functions. And I would urge you to go to the QUAKE-W engineering book for the details as to how we have arrived at these sample functions. I won't take the time here to go into the detail as to how these sample functions were provided. We will simply make use of them here in this illustrative example. Very generally, the shear modulus is a function of the effective confining stress or the overburden stress. As a easy thing to remember is that G tends to be proportional to the square root of the stress state. In other words, the relationship usually has some form of a curve, but the most important thing is that the soil stiffness increases as the overburden stress or confining stress increases. In QUAKE-W, we have set it up in such a way that Gmax is a function of the effective overburden stress. So here's a typical relationship. So here is the effective overburden stress. Once the effective overburden stress is known in an element, we can then come in and find the shear modulus for that particular element. We're going to define this function for our illustrative example here and show how we can use our sample functions and manipulate this function. But it's important to recognize that soil stiffness, particularly granular materials, the soil stiffness increases as the confining stress increases. And in GeoStudio or QUAKE-W, we have set it up in such a way that Gmax is a function of the effective overburden or effective vertical stress. To those of you who are familiar with the theory of elasticity, know that there is a relationship between the shear modulus and the Young's modulus. But when we do a quake dynamic analysis versus a sigma static analysis, it's important to recognize that the Gmax modulus for a dynamic analysis is not the same as the soil stiffness E for a sigma static analysis. The Gmax tends to be much higher than the Young's modulus suitable for a sigma static analysis. And so we have to be careful that we do not use this relationship between G and Young's modulus. Very simply or briefly, the Young's modulus for a static analysis is a lower value as opposed to the shear modulus for a dynamic analysis, which is a small strain value and tends to be much, much higher than the value that we would use in a sigma analysis. So we need to be careful in how we select the shear modulus and the Young's modulus. If you have data on the Young's modulus, you cannot simply use this relationship to get the shear modulus. The shear modulus needs, for a quake analysis, needs to be determined independently of a Young's modulus suitable for a sigma static analysis. Then during the earthquake shaking, and as the ground moves, the soil softens, that is, becomes less stiff in response to the cyclic shear stresses. And consequently, we have to modify Gmax in response to the shear stresses, as I mentioned a little bit earlier. Once again, as with the actual stiffness G, we provide estimation techniques in the software, and the details of these estimation techniques are again provided in the QuakeW engineering book. So the function specifies a reduction as a ratio of Gmax. So we have G times some ratio times G max. And what this function gives us is this particular ratio. So now that we have noted the types of information that we need for a dynamic analysis, a quake equivalent linear type of an analysis, we can go back to GeoStudio, create these material properties, and apply them to the regions. So the next step is to set up a dynamic analysis, and then we are going to proceed with defining the soil stiffness, damping, and softening properties. To begin with then, under Key in Analyses, we click on Add, a Quake Analysis, Equivalent Linear Dynamic. Our initial static stresses are going to come from our initial conditions, and the static stresses are going to come from our parent, and the pore water pressures are going to come from our parent, and we are going to do an equivalent linear type of an analysis. We now need to define our stiffness properties under Key in Materials. And for the foundation, I have already defined a foundation G function. Clicking on this ... button, we have here a G max function. And what I have done here, if we click under Estimate, I selected from the granular granular soil category here. And from the default values, I selected loose sand. These parameters, maximum depth is just a mechanism for controlling the extent of the horizontal axis in this graph. This is just a means of a smaller number would mean a lower stress range, a higher number would mean a larger stress range. K is a modulus number, and I would once again refer you to the QUAKE engineering books to study the meaning of the modulus number. And K naught is just a means of using a stress in order to compute this function. And to all of you who have been familiar with slope, seep, and sigma, you know how to manipulate this function. All of these are data points. You can delete certain data points, or you can add to them, move them, modify them, and so forth. So in this particular case, I clicked on OK, and it regenerated the function. But I decided in this case that I would make my minimum modulus 20,000. So I can type in the y-intercept edit box 20,000, and it shifts up the entire curve. Now it's important to recognize that what this curve is telling us is that we will have a minimum modulus of 20,000. And if we look at this part of the graph, we see we will have a maximum of 80,000. We can say a particular range here where we go from 0 up to, let's say, 300 kPa. And as a result, we can see we have a minimum value and we have a maximum value. In between, we have some curved relationship. Now, this is a data point function, and you can specify your own data points or modify these estimated data points, but this is the way we control the definition of the soil stiffness for a dynamic analysis. So I have defined two Gmax functions here, one for the foundation and one for the embankment, which I'm going to use for all the other materials. Notice that in this particular case, we used a granular soil category, but I selected a function for a dense sand. And I have made the minimum 40,000 kPa and the maximum 180,000 kPa. So now we have two G functions, shear modulus functions. We need a damping function, so once again clicking on the ... And once again, in this particular illustrative example, I only have one damping function. And once again, you can go to the QUAKE engineering books for the empirical formulas used to develop this function. But if we click under estimate, the only parameters that you can define is some confining stress. It's not sensitive to the confining stress. You can have a low number or a high number. We have defaulted it to 100, and then whether there is some plasticity in the soil or not. Nonetheless, for this illustrative case here, this is the damping function that we are going to use, and we see that the damping, as I mentioned earlier, increases as the cyclic shear strain increases. Finally, we need to define a G reduction function. And once again, in this particular case, I have two functions, but in actual fact, they are identical. The G reduction function is estimated in exactly the same way through some empirical formulations as the damping function. In this case, I have two functions here, but they are actually identical. So we have, for the foundation material, we have a G max function, a damping function, and a G reduction function. We need to do this for all the soils. For the dam embankment itself, I have selected the G function for the dam, but we're using the same damping function. However, we are using the G reduction function for the dam. I'm using the same materials for the superficial crust and the granular drain as I did for the dam embankment material itself. And so you can see here we have the G max function, the damping ratio function, and the G reduction function for all of the materials. And as always, when we create a new analysis, then we have to say draw materials. We have the dam, and then the granular drain, and the foundation, and the superficial crust. Now at this stage, just to review some other features, we can go and say View, Object Information, and you can click on a region and you can get information about that particular region. And so we are doing an equivalent linear type of analysis. Here's some of the stress strain data, and here is the Gmax function, some information, and so you can spot check that the definition is as intended. We need to define the boundary conditions for the dynamic analysis, and as I noted earlier, we make the bottom of the boundary fixed, so we have a fixed boundary condition in the X and Y direction at the base of the problem. And in a dynamic analysis, we usually fix the vertical direction at the ends, but allow the ends to move horizontally, but they are fixed in the vertical direction. Once again, allowed lateral motion, but is fixed in the vertical direction. So now we have set up a dynamic analysis, defined the boundary condition for the dynamic analysis, and we have defined our stiffness and damping properties for the materials for the equivalent linear analysis.